Hello, hello, hello. This is Nicholas on this lovely Thursday afternoon, wanting to talk to you today about Green's theorem. And ideally, I'm talking to you about this so that I can eventually build my way up to Cauchy's integral theorem and the Cauchy-Riemann equations in complex analysis. So first, Green's theorem. So I'm trying today to give you, I guess, more of an intuitive understanding of what it is. I'll do a little computation, but not too much. Now, Green's theorem is basically the idea of relating a line integral to a double integral. And I proved Green's theorem for you using the general Stokes theorem and differential forms, but that's really not the way it would be taught in a standard Calc 3 class, and so it's kind of somewhat inaccessible. The way it would normally be taught is if you've got something with a closed curve, a simple closed curve, it's nice enough. So in other words, it's piecewise smooth. It doesn't have any like infinitely many corners, like some sort of stochastic boundary or something like this. And we need the condition that it's closed specifically so that there is a region, which I'll call D, that is enclosed by the boundary, which we denote with the del symbol delta D. And more specifically, we say that the region has to be positively oriented. And really at the heart, this is just kind of a generic convention. But when we say positively oriented, we mean that when we walk along the region, it lies on our left. So in other words, there's two ways that we can walk around this region, like this, or the opposite way, like that. And the question is, like, which orientation would we like to choose? And if we look at it, right, if I go along this way, every time if I am a person like walking along this boundary curve, the region D is on my left. And so the correct positive orientation means that the curve, we would walk around it this way. Now, if I have this closed region, and it is important that the region is closed because otherwise how could we take a double integral of like an open region, right? Then basically what we can do is use the idea that the whole heart of Green's theorem is that the total change on the outside, right, if I'm going to go along this whole curve, is the sum of the little changes on the inside. And that's very wishy-washy, so I'll explain what I mean more in a second here. Let's say, for example, I have the same kind of lima bean region, whatever, and I just chop it up twice, right, like here or something like that. And now, if I am going to take the line integral over this whole boundary curve, del D, what I instead could do is take the line integral over two separate boundary curves, right, over this boundary curve, right, by this first region, and then add it to the boundary curve over this second region, right? And that's still going to cancel out any sort of overlap here, right? Because in this way, I'm doing the line integral like that, but in this way, I'm doing the line integral like that. And I'm going exactly the opposite ways when I actually work out the algebra and do my parameterization and all this stuff. And so all the overlap cancels out. And what I am left with is the whole boundary curve again. And so, in fact, I can keep doing this, right? And the idea is that we chop it up into, really, really small slivers, right? We're basically building our way towards this Riemann sum. And rather than integrating along the whole curve, I chop my region up and I integrate along the little curves within the region, right? So like, I'm not going to draw all the arrows here, but imagine inside each one of these little regions, I do a line integral along all of those curves. And what's going to end up happening is that all of these overlap regions are going to cancel out. In other words, at some point, we're going to be doing a line integral, and one way will be going like this, for example, but the other way will be going like that. And so they're going to be opposite parameterizations, and we'll get a big fat zero. Now, what does this actually become, right? We have a line integral over the boundary of our region of, and there's two ways we can write this. Something that is confusing at first is all the different notation, but typically you'll see it as written as f dot dr, where f is your vector field, or you'll see it written like this, and this is more suggestive of the language of differential forms, and whereas this is more suggestive of like work done needed to move a particle from point A to point B. Anyways, so this line integral becomes now a double integral over the area enclosed by our boundary curve. So this is D. And now what are we actually going to be integrating, right? So it's a Riemann sum of what? Well, it's all of these little curls right here, right? If you know of the curl of a vector field, it's the tendency for some basically mini point mass, loosely speaking, to want to rotate about this like infinitesimal circle, or if you're in 3D, an infinitesimal sphere. And that's exactly what we're measuring, is all these little curls, right? If I draw all these arrows, it's the curl of the vector field. That's geometrically what the curl means. Just like how the divergence is, the tendency for the vector field, if you think of it as like fluid flow, for the fluid to flow out of a infinitesimal circle source or into it, right? That is intuitively what we mean by curl. And if you want more intuition on this, I would highly suggest watching 3 Blue 1 Brown's video on, it's called like Curl and Divergence, the Language of Maxwell's Equations. It's a really great video. Anyways, we're basically taking a Riemann sum over this whole region of just the curl of our vector field. And so it's the curl of f dA. And that's Green's theorem. There's really not much to it. Now, typically you don't see it written this way. And also typically Green's theorem is, that the curl is typically a 3D concept. We don't normally talk about curl in 2D. But if we use the 3D definition of curl, how to compute it, right? It's this weird matrix. On the one hand, we can think of it as del cross f, where del is like this pseudo operator, the pseudo vector, partial with respect to x, partial with respect to y, partial with respect to z. Oops. And so it is this matrix, ijk, right, cross product. The first, quote, vector is the partials, and the second vector is the components of our vector field. In this case, f would just be like p, q, 0, because it exists wholly in the xy plane. So the z component of the vector field is 0. P, q, 0. And what do we get when we take this determinant? We get I hat times 0 minus 0. Remember that p and q are both functions of only x and y. So that's a 0 minus j hat times 0 plus k hat times. And then this is where we get stuff, the partial of q with respect to x minus the partial of p with respect to y. And we can replace that in the integrand. That's the partial of q with respect to x minus the partial of p with respect to y dA. And that's typically how you would see Green's theorem written when you first learn it in a Calc 2 or Calc 3 class. Now I will give one example because it's a neat extension of what's known as the shoelace theorem. So let's say that our vector field f is 0x. And let's say that we're integrating along a unit circle. We're doing the line integral of this vector field over the unit circle, right? So the line integral setup would be the boundary of D of f dot dr, and we're going to change this to a double integral over D of the partial of q with respect to x minus the partial of p with respect to y dA. All right. And now what is the partial of q with respect to x minus the partial of p with respect to y? This is p is the first component, q is the second component. So the partial of q with respect to x, that's just 1. And the partial of p with respect to y, well, that's just 0. So the integrand just becomes dA. And it's just the area of a unit circle, right? The double integral of dA is just the area of your region. And so this integral just becomes pi. So hopefully you can see that it's a lot easier to, when your region is closed, to evaluate line integrals as double integrals using Green's theorem. And another thing I'd like to point out is that it wasn't just coincidental that this ended up giving us the area. In general, you can use Green's theorem to calculate area of any 2D region, right? Even if you're not even talking about vector fields, you can just kind of postulate that, oh, well, let's say that we're taking the line integral of this region, the region that we want to find the area of. So if we want to find the area of some arbitrary region, and of course, area only makes sense if the region is closed, right? You can't talk about area for open regions. And let's say this is the boundary curve of our region. And, this is purely a geometric problem now. We don't even have vector fields to consider. But the trick is to kind of, well, let's just throw in a vector field. And then when we do that, this answer that we get will actually represent the area. And we can just throw in any vector field. It has to be a special type of vector field. It has to satisfy the partial of q with respect to x minus the partial of p with respect to y has to be equal to 1. And then in that case, right, when this gets replaced with a big 1, you just get the double integral over d of dA. And so that double integral will represent the area of your region. And I have done a video on this with Shoelace's theorem and how it extends it to any simple closed curve. The only problem usually is that you have to find a parameterization, right? This circle, it's very easy, right? R of t, your parameterization would be, it would just be cosine t, sine t, and t would go from 0 to 2 pi. And, let's suppose for a second we didn't even know what the area of a unit circle was, but we somehow knew calculus 3. How could we find the area of this unit circle? We could suppose that this unit circle exists in this vector field 0x, and we could find the line integral over the boundary of d of f dot dr, which would be the regular integral from 0 to 2 pi of 0, and then x is cosine t, dotted with r prime, which is r prime of t is negative sine t cosine t. So negative sine t cosine t dt. And then when we do that dot product, we get the integral from 0 to 2 pi of cosine squared t dt, which turns out to be pi. And then that's using the line integral, and now using the double integral to actually verify that Green's theorem is true, right? We get the double integral, and it's just dA, right? Because that was the whole point of choosing this vector field, is so that the integrand just reduces to 1 dA. And then now we need to integrate this region D, and the best way would be to convert to polar, right? So r goes from 0 to 1, theta goes from 0 to 2 pi of r dr d theta. And if you work out that integral, it happens to be pi. Now, again, if we were going at this from a purely geometric point of view and we just wanted to find the area of a circle, we wouldn't even be talking about vector fields. But it's kind of neat that introducing vector fields to just a purely geometric problem lets us learn something about the geometry in question. And with that, we're done.